for today. Okay, so we're now ready to begin chapter 22, which focuses a lot on enolate chemistry and the reactions of enolates and enol derivatives. So before we start discussing the reactivity of enolates, it's important for us to refresh our knowledge of some common reactions of carbonyls. First, let's talk about some nucleophilic addition reactions. There are two main types of nucleophilic addition reactions, either direct 1,2 addition that occurs when we have quote unquote hard nucleophiles. What's an example of a hard nucleophile that we've seen in this course? What's an example of a nucleophile that prefers 1,2 addition? So when we saw previous examples of addition reactions, a Grignard reagent is a really common hard nucleophile. So for example, phenyl magnesium bromide would be a textbook hard nucleophile that prefers to add directly to the carbonyl via 1,2 addition. So from here, we can isolate an alcohol, and depending on the nucleophile involved, they each have a unique name. Let's look at the other case, which is 1,4 addition, which is addition to the beta carbon of an alpha beta unsaturated aldehyde or ketone. We also can call these unsaturated aldehydes or ketones. In the case of the ketone, we call these enones. In any case, 1,4 addition is addition to the beta carbon of an unsaturated aldehyde or ketone. Now, what's interesting about this 1,4 addition pathway, it's preferred when we have quote unquote soft nucleophiles. And examples of soft nucleophiles could be amines. We can look at organocuprates, thiols. Generally, most nucleophiles where your electron density is delocalized over a relatively large atom, or in cases where you're not dealing with a hard carbon-centered nucleophile, you're going to see a preference for 1,4 addition. Now, what's interesting about this 1,4 addition pathway is it generates a carbon-centered anion that we call an enolate. We've seen these enolates and these Enol Tautomers in previous mechanisms, but they've always just been protonated. We can protonate these enolates with acid and just get our neutral isolable 1,4 addition product. What we're going to be talking about this class session are the patterns of reactivity for these enolate ions and how we can leverage enolates to prepare highly complicated structures. So does this review make sense to everyone? Does this review of addition reactions make sense? Does everyone see the distinction between 1,2 and 1,4 addition? And do these mechanisms look familiar? Wonderful. So let's continue on now. And let's talk about the alpha position. So the carbon next to the carbonyl group is designated as the alpha position. Electrophilic substitution can occur at this position through either an enolate ion or an enol. So the enolate is the anionic species, while the enol is a neutral tautomer. Both enolates and enols can react with electrophiles to generate substituted products at the alpha position. The main thing I want you to take away from this is that the alpha position of carbonyls is reactive. Carbonyls can be converted to enolate ions in the presence of base. So for example, a base can pull off this proton to form an enolate. Or the carbonyl compound can tautomerize, usually in the presence of acid, to the enol. And both the enolate and enol can react with electrophiles to yield substituted products. Does that make sense to everyone? Okay, so let's talk a little bit more about how we access the Enol Tautomer under acidic conditions. In previous chapters, we discussed this idea of Keto-Enol Tautomerism. So isomeric compounds that can rapidly interconvert via the movement of a proton are called tautomers. And this phenomena of interconversion between tautomers is called tautomerism. Enols can rearrange to the isomeric ketone via the rapid transfer of a proton from the hydroxyl to the alkene carbon. Generally, the keto form is more stable in most cases compared to the enol form. One reason why stems from the fact that this carbonyl is a relatively stable bond and a relatively stable functionality. And as a result, the carbonyl is preferred over the corresponding enol tautomer. Okay, now tautomerism can be catalyzed by either acid or base, and we're going to look at the mechanism of acid and base catalyzed tautomerism next. Okay, so under acidic conditions, probably the most reasonable mechanism is first direct protonation of the alkene to make a carbocation. Although this carbocation looks a little bit unstable at first glance, you'll notice that it's adjacent to a donating oxygen atom. And so we can kick that lone pair down to generate a resonance structure. One thing I would like you to note is I use resonance arrows for this step because there's no formal bond breaking or forming event. From here, all we have to do is deprotonate our carbonyl oxygen and we get our ketone or keto form isolated cleanly. Does this mechanism for acid catalyzed tautomerization make sense? Any questions on this mechanism?
Does the carbocation prefer to be on that carbon just because it's like tertiary, or?
It's a combination. Well, first, it's adjacent to a stabilizing electron donating oxygen atom. So if we protonated instead of the alpha position directly at the carbonyl carbon, we get a less stable carbocation.
Okay. Okay.
Further, if you think about this mechanistically, you can draw this step as you kick down this lone pair to form your carbonyl and you protonate the alpha position. That's another way you can view this protonation step, which helps demonstrate why the alpha position is protonated. It's the most electron-rich position, and protonation of the alpha position yields a very stable carbocation.
Okay.
Did that answer your question?
Yes, thank you.
Perfect. Okay, let's talk about the tautomerization mechanism under basic conditions. So in this case, starting from the keto form, base will pull off a proton and will generate our corresponding enolate. From here, rather than protonating our enolate at carbon, we can protonate our enolate at oxygen and generate the corresponding enol tautomer. Does this mechanism of tautomerization under basic conditions make sense? Okay, so let's try to apply what we've learned and let's try to draw a mechanism for the following reaction. So in this case, we have cyclohexanone. We're treating it with hydrochloric acid, and that gives the enol tautomer. Let's try to apply what we've learned and take about 3 to 4 minutes to try to draw out a full mechanism for this reaction. And let's just make sure our drawn mechanistic steps match the reaction conditions. So if we're treating this compound with hydrochloric acid, are we under acidic or basic conditions? That is really key. We're under acidic conditions, right? So the tautomerization mechanism should be the acidic tautomerization mechanism. Okay, so let's work through this example for about 3 to 4 minutes. And I'd like students to share their proposed responses as photos of their written work or just written explanations for this mechanism in the chat. You can also share the steps for this mechanism verbally, and I'd be happy to annotate them out on the class whiteboard. Or you can annotate your mechanism directly onto the class whiteboard, so that way we can provide commentary and help advance our discussion. If there are any questions that I can address as we work through this problem, don't be shy to ask in the chat or verbally, and I'd be happy to help answer any questions that you have. So let's work through this example for about 3 to 4 minutes, and then I'd like some students to start to volunteer and share their mechanism on the class whiteboard. So we have hydrochloric acid. Okay, so they're showing protonation of the carbonyl. If you're drawing protonation, I would draw your arrow from the lone pair to the hydrogen, just to show it's being used to form an oxygen-hydrogen bond. So after protonation of our carbonyl, one way to think about this to make it easier to see is I would try to draw the resonance form for this carbonyl. What is a resonance form of this carbonyl that may make it a little bit easier for you to see the next step for this mechanism? So eventually we need to form a carbon-carbon double bond. So we need to essentially lose a proton from our alpha position. There's one too many lone pairs on that oxygen. I would just erase one of the lone pairs. So what would a resonance form of this compound look like? Not a tautomer, just a resonance form. This may help us see the next step. Yep. Okay, so we kick a pair of bonding electrons up, and that gives us a carbocation. Now, as we've learned when we talk about carbocations, would you be able to draw that carbocation in so that way we can discuss where is the positive charge? So if we kick this bonding electron up from our carbonyl carbon, where would the positive charge end up? Yep, exactly right. Now, as we learned when we talked about, for example, the E1 reaction, when you have a carbocation, is it easy to eliminate and form an alkene on that carbocation? Is it easy to eliminate these adjacent hydrogens? What do we think? So if we have a generic carbocation and we have a hydrogen adjacent, is this elimination process where we pull off this hydrogen easy or hard? If we have a carbocation and we have protons adjacent, this elimination is super easy. Okay, so with that in mind, let's draw almost like an E1-like mechanism. So would anyone be able to draw out the arrows? Sure, sure. And that's not a problem. You don't even need water. Your substrate could serve as the base. You can also use chloride. That's less common. You can even show another equivalent of this ketone serving as the base. Any generic base would do. You can draw out the ketone. I guess there's probably going to be a little bit of water, though you don't need water necessarily. Yep, so we pull off the proton, we eliminate, and let's draw the final structure of our product. Perfect. After elimination, let's draw the structure of the product exactly as is. So we eliminated this proton, we formed a carbon-carbon double bond. Would you be able to draw the structure of the product based on the arrows that you drew for the mechanism? Yep, perfect, perfect. So the student proposed mechanism looked great, and it's nice to see students sharing their thoughts in the chat to help advance our discussion. Okay, so let's talk about the mechanism for this reaction. So you don't need necessarily an external base such as water. It makes the reaction easier, but you can run this even with potentially anhydrous acid and you'd still see some tautomerization. So for the first step, we're protonating our carbonyl oxygen. Okay, we've now activated this alpha position. I'm going to draw the resonance form just this once to help us visualize why this elimination occurs so readily. As we've learned previously, elimination involving protons adjacent to a carbocation occurs quite readily. And for our base, even another equivalent of substrate can pull off our proton, and that in turn gives us our desired isolable Enol Tautomer. And the beautiful thing about the way that we've drawn this mechanism here is that it shows that the reaction is catalytic in acid because we donate a proton to our substrate, and at the end of our reaction, we pull off an equivalent of a proton. Does this mechanism make sense to everyone? Okay. So let's work on another example. So this time we're dealing with the same substrate, cyclohexanone. This time we're treating it with sodium hydroxide, and I'd like us to draw out the mechanism for this tautomerization reaction. And let's just make sure we're all on the same page here. Are we under acidic or basic conditions? Basic, yep. So with that in mind, let's try to draw out a full mechanism for this base catalyzed tautomerization reaction. So in this case, our basic sodium hydroxide reagent will pull off our alpha proton. That'll in turn generate the enolate anion. And to complete this tautomerization to the enol form, what happens next? We're going to protonate the enolate, and that gives us the enol form. Does this make sense to everyone? The student proposed mechanism looks great. So let me just re-annotate this mechanism so that way it's all saved on the class whiteboard. So we have our carbonyl, treatment with sodium hydroxide. We get deprotonation of our alpha proton, which is an acidic proton. That in turn gives us our enolate. From here, we can protonate our enolate with the equivalent of water that we just generated. And that in turn gives us our Enol Tautomer. I would comment though, under basic conditions, you're far more likely to have the more reactive and nucleophilic enolate ion react rather than tautomerize to the enol form and then react using the Enol Tautomer. Does this mechanism make sense to everyone? Okay, so let's keep going then. And let's talk a little bit about enols and enolates. The enol tautomer is usually present to a very small extent and generally cannot be isolated as a single pure compound. You can observe the enol tautomer for some compounds by proton NMR and by IR in solution. What's important to note is even though we generate a small amount of the enol tautomer, the enol tautomer can serve as a reaction intermediate and can serve as a nucleophile for many common carbonyl alpha substitution reactions. Now, the enol tautomer is very different than an enolate. Under strongly basic conditions, this is no longer an equilibrium. We're functionally driving the equilibrium almost entirely to the product side. And we can generate what's known as an enolate via deprotonation of our alpha position. The exact base required for enolate formation depends on the pKa of the alpha position. And that's important to keep in mind. Generally, you'll need quite a strong base with a conjugate acid pKa of 35 or more, generally. Does everyone see the distinction between an enol and an enolate? Enolates are anionic species that are usually generated irreversibly via deprotonation with strong bases. Does this make sense to everyone? Okay, so while we're on the idea of enolate formation, let's talk about the acidity of common alpha hydrogen atoms in the context of enolate formation. Carbonyl compounds are weak acids, and the presence of a carbonyl dramatically increases the acidity of the alpha position. So for example, acetone has a pKa of around 19.3, while ethane has a pKa of around 60. So as we can see, the presence of this carbonyl has dramatically increased the acidity of our alpha position. Now, what we notice and what we prepared here is a table of Pka values. There are a few important things to appreciate from this table. First, I'd like you to note for carboxylic acids and amides that if there is a free acidic proton on your carboxylic acid or amide, those protons can be removed preferentially by bases. You're not going to deprotonate the alpha position. Instead, you're going to deprotonate your oxygen or nitrogen atom because that proton is more acidic. The other thing I'd like you to note is we have a general hierarchy based on the electron withdrawing character of our carbonyl or carbonyl equivalent. We see that the alpha proton pK can vary substantially for different carbonyl groups. Generally, the more electron deficient your carbonyl equivalent, the more acidic your alpha proton will become. That's why the nitro group has the most acidic alpha proton, while aldehydes are the next most, followed by ketones, esters, nitriles, and amides. Another thing to note, when we have two electron withdrawing groups, we notice that the alpha position of acidity increases dramatically. So beta ketoesters can be deprotonated with substantially weaker bases because this alpha position is substantially more acidic. Does this discussion of pKa make sense to everyone? I'd like you to just have this table as a reference to help you decide what base is necessary to complete and to generate an enolate for many of these carbonyl derivatives. Now, to add a little more context here, let's talk a little bit about the reactivity of enols. And let's just highlight a really important point. When we look at an enol and we draw out a resonance structure for this Enol Tautomer, we notice that the alpha position is quite electron rich. Another thing that I would like you to note is when we think about generating an enol or enolate, only the hydrogens at the alpha position to the carbonyl are appreciably acidic. As a result, we can get regioselectivity for these alkylation reactions because only the alpha position can be effectively deprotonated with base, and we can only generate enols via tautomerization of our alpha position. We won't see reactivity at our normal alkane hydrogens. Does that point make sense to everyone? Only the alpha protons are sufficiently acidic, and as a result, we only see reaction at the alpha position. Okay, so let's keep going then, and let's talk about general mechanisms of carbonyl alpha substitution. So first, under basic conditions, we deprotonate our alpha position and we make an enolate. Once we have the enolate reacts with our electrophile and we form a bond between our alpha position and the electrophile. That's it. One thing I would like you to note, most electrophiles react at carbon rather than oxygen. There will be some exceptions, such as silyl chlorides, where you will see reaction at the enolate oxygen, but generally most electrophiles that we'll see for these reactions of enolates will react and alkylate at carbon. So all of your alkyl halides, carbonyl compounds will generally react with enolates at the nucleophilic carbon. And that's partially because we can retain this quite stable carbonyl functionality. Does this mechanism make sense? And does our discussion of regiocontrol make sense? Any questions on the mechanism for enolate alkylation under basic conditions? Okay, let's talk about the mechanism of alpha substitution under acidic conditions. So in this case, we have our Enol Tautomer. That's the actual reactive species. Our Enol Tautomer reacts with our electrophile at our nucleophilic enol carbon. We form a bond between our alpha carbon and the electrophile. And then as a cleanup step, our base or reasonably basic species in solution will pull off a proton to regenerate our neutral carbonyl compound. Does this mechanism of enolate alkylation under acidic conditions make sense? In this case, under acidic conditions, we are alkylating the Enol Tautomer. Any questions on these mechanisms? Okay, so let's keep going and let's talk about a very common reaction of aldehydes and ketones, which is the alpha halogenation of aldehydes and ketones under acidic conditions. So aldehydes and ketones can be halogenated at their alpha positions via reaction with chlorine, bromine, or iodine in acidic solution. Because we're under acidic conditions, it's clear that we're having to go through an enol tautomer. In terms of the mechanism for this reaction, our first step, starting from our parent ketone, is to tautomerize this ketone to the enol form. So after tautomerization to the enol tautomer, we now have our nucleophilic species that we can react with our electrophilic halogen. From here, our nucleophilic enol will react with the electrophilic halogen to form a carbon halogen bond. Finally, as a cleanup step, the reasonably basic species in solution will pull off a proton, and that gives us our alpha haloketone. In this case, since we used chlorine as our electrophilic halogen source, we get our alpha chloroketone. Does this mechanism for acid catalyzed chlorination and bromination of ketones and aldehydes make sense? Okay, if we don't have any questions, let's try to apply what we've learned to the following example. So let's take about 3 to 4 minutes to work through this example. In this case, we're asked to draw a mechanism for this reaction. In this case, we're showing the alpha bromination of cyclohexanone under acidic conditions with bromine and hydrobromic acid. So as we work through this example, I'd like students to share their proposed responses in the chat verbally or annotated on to the class whiteboard. And if there are any questions as we work through this example, don't be shy to ask them in the chat or verbally, and I'd be happy to provide input. So we have the student drawing protonation of your carbonyl. Yeah, you can use another equivalent of carbonyl as your basic substrate, or you can use an equivalent of halide. Either would be fine. So after protonation of our carbonyl, we'll tautomerize this carbonyl from the keto to the enol form via deprotonation of the alpha position. From here, we now have our reactive Enol Tautomer, which can react with electrophiles such as bromine. So our enol tautomer will react with bromine, and that gives us our alpha bromo ketone. From here, we just have one cleanup step. Where we pull off and deprotonate our carbonyl oxygen, and that gives us our neutral isolable alpha bromo ketone. Yep, perfect. The student proposed mechanism looks great. So let me clear annotations and let's redraw this mechanism for our reference. Okay, so we have our carbonyl and we're going to tautomerize this carbonyl from the keto to the enol tautomer via initial protonation of our carbonyl oxygen. From here, this has activated the alpha position. So now even any reasonably basic species in solution can pull off our alpha proton and tautomerize this species to the desired reactive enol tautomer. From here, now that we have our nucleophilic enol tautomer, it can react with an electrophilic equivalent of bromine to generate our desired alpha bromo ketone. However, we don't get the desired product directly. We still have one last cleanup step where we take this protonated alpha bromo ketone and we simply pull off our proton to generate our neutral isolable product. Any questions on this mechanism for the acid catalyzed bromination of a ketone or aldehyde? Any questions on this mechanism before we move on? Okay, so let's keep going on then, and let's talk a little bit about the kinetics of enol formation. When we study this acid catalyzed halogenation, these reactions show second order kinetics with a dependence on the concentration of ketone and acid. That's a bit odd when you think about it. What is missing from this rate law? What is missing from this reaction rate expression? Does anyone notice something that's missing? For an acid catalyzed halogenation, what is missing from this expression that seems a bit counterintuitive at first glance? Sure. The halogen itself, right? So what we found, if you do kinetic studies on this reaction, is that the halogenation depends only on the concentrations of ketone and acid. The rate of halogenation is independent of the halogen's identity and concentration, and the halogen is not involved in the rate limiting step. So the rate limiting step is actually formation of your reactive enol tautomer. Once you have the enol tautomer, the reaction goes quite quickly. Does that discussion make sense to everyone? I thought it was pretty interesting. Okay, so let's keep going then. Another piece of evidence for rate limiting enol formation, if you treat a ketone or aldehyde with D3O+, the acidic alpha hydrogens are replaced by deuteriums. Further, the rate of deuterium exchange is the same as the rate of halogenation. And this stems from the fact that the rate limiting step is not actually the reaction of your enol tautomer, but the formation of the enol tautomer. The tautomerization step is the rate limiting step for this reaction. Okay, so the reason why I talk about deuterium labeling is it serves as a very useful tool to identify reactive alpha positions and sites of reactivity under acid-base tautomerization reactions or sites of reactivity under both acidic and basic conditions. So essentially, if you see deuterium incorporation at a position under acidic and basic conditions, you can begin to think about whether that site could be reacting with certain electrophiles under acidic or basic conditions. So for example, for this ketone, the alpha position gets labeled with deuterium under acidic conditions because the alpha position can be readily tautomerized, the corresponding enol tautomer, and then that enol tautomer can be protonated. So when you see deuterium incorporation, when you're talking about enol or enolate chemistry, what I want you to think is that site can potentially react with an electrophile, or at the bare minimum, that site is labile under acid-base reaction conditions. So with that context in mind, let's take a look at the following molecule and let's try to draw out what positions would exhibit deuterium substitution under the reaction conditions. And I'd like you to presume that we're using relatively dilute acid. So we're not going to high temperatures. So what positions in this molecule would we expect to see deuterium incorporation? Which of these positions can we generate a substantial amount of enol tautomer under acidic conditions? So let's take about 3 to 4 minutes to work through this example. And in this case, it would really be best served if you annotate on or circle what carbon positions in this molecule would you expect to see deuterium incorporation. And as we work through this example, don't be shy to ask questions in the chat or verbally, but I'd really like students to share their thoughts and responses. To help students convey their responses, I'll label some carbons. And you can even type in the chat, what carbons would you expect to see deuterium incorporation? So we have students indicating positions 2 and 6. Yes, these are alpha positions relative to a carbonyl. Any other positions, any other acid labile positions in this molecule? So when we looked at that table of acidic functional groups and we looked at the table of alpha proton acidities, is there a carbonyl equivalent? 4, position 4, right? And when we think about a nitro group, these alpha positions have a pK of around 9. So you can see similar tautomerization under acidic conditions for these nitro groups. As such, we would see deuterium incorporation at all of our indicated alpha positions, 2, 4, and 6. That's really important to think about because if you tried to do an enolate alkylation reaction, or if you tried to do any sort of enol or enolate chemistry on this substrate, you would notice that this alpha position to our nitro group is reactive under enolate forming conditions. Does this example make sense to everyone? The alpha position to carbonyl equivalents are labile and can be labeled with deuterium under both acidic or basic conditions. Does this example make sense? Are there any questions I can address on this example? Okay, so let's talk a little bit about how we can use alpha bromoketones and alpha brominated carbonyl compounds for further reactions. So alpha bromoketones can undergo elimination reactions under strongly basic conditions at high temperatures. So alpha bromoketones can be dehydrobrominated upon treatment with base to yield alpha, beta, and saturated ketones. This reaction follows an E2 elimination pathway. So in terms of the mechanism for this reaction, once we have our alpha bromoketone, and I'm just going to put some arbitrary stereochemical labels here. So we have our alpha bromoketone, our base, which in this case is pyridine, though you can really use any reasonably non-nucleophilic base. We'll pull off a proton and we'll simultaneously form our alkene and eliminate and lose our equivalent of halide. Now, this is an E2 reaction, so this elimination is a concerted process, and the proton that we remove during elimination must be anti-periplanar to our leaving group. Does everyone notice how the hydrogen and bromine are trans-diaxial or anti-periplanar in this mechanism? Does that idea make sense? An E2 reaction requires a certain orientation of your hydrogen and leaving group. Further, the E2 reaction is stereospecific. So if you have a defined stereochemistry for your installed halogen, you can get a defined alkene geometry. Okay, so let's talk about one other aspect of this mechanism. So the elimination of bromine in alpha bromoketones to yield an enone follows a typical E2 mechanism. That much is clear. Let's try to answer the question, why do we not see an E1 pathway? Why do we not see an E1 mechanism? So why would we not see loss of bromine to form a carbocation? Why does this not occur? Would anyone like to offer a reason why? So the traditional mechanism for dehydrobromination follows an E2 pathway. Why do we not see an E1 pathway? Does this carbocation that we'd make under a proposed E1 pathway, is that carbocation remotely stable? No. And as a result, we would not expect to see an E1 mechanism. The barrier to form that carbocation is insurmountably high when we're trying to form a carbocation adjacent to a strongly electron withdrawing carbonyl. Does this discussion make sense to everyone? And does this mechanism for dehydrobromination make sense? Okay, so let's keep going then. So in this case, we're asked to predict the product of the following reaction and draw a mechanism for this reaction. So we're treating alpha bromocyclopentanone with pyridine and heat. So in this case, I'd like us to predict the product from this reaction and then draw a mechanism for this reaction. So let's work through this example over the next 3 to 4 minutes. And then I'd like students to share their proposed responses in the chat, verbally, or annotated directly onto the class whiteboard. So we have some students predicting that we'd be able to generate cyclopentanone. So let's try to justify this predicted product with a detailed mechanism. So in this case, we have the student drawing out and trying to show that when we eliminate our equivalent of bromine, when we lose our halogen, which is bromide, this elimination occurs via an E2 pathway, which requires an anti-periplanar arrangement of our hydrogen and leaving group. Yeah, so this student proposed mechanism and predicted product look perfectly reasonable. Let's just redraw this mechanism on the class whiteboard so that way everything's saved for our reference. I'm just going to put an arbitrary stereochemistry label. In future problems, your substrate may have a defined stereochemistry. So you'll have to carefully note that when you're drawing out your mechanism. let's pause really quickly so I can reset OneNote. Okay, so continuing on, pyridine will pull off our anti-periplanar hydrogen, and we have a concerted elimination and loss of our leaving group to give cyclopentenone. So this is a textbook E2 mechanism. Does this problem make sense to everyone? And does this mechanism make sense? Any questions on this mechanism before we move on? Okay, so let's keep going then, and let's talk about the alpha bromination of carboxylic acids. And this mechanism is fundamentally different than the patterns of reactivity for ketones and aldehydes. And that really stems from the fact that carboxylic acids have a highly acidic proton. So carboxylic acids, esters, and amides do not enolize efficiently. Thus, in order to effectively brominate the alpha position of a carboxylic acid, first, the carboxylic acid is converted to an acyl bromide, and then from there, the acyl bromide can then be converted to the Enol Tautomer and brominated under the reaction conditions. Thus, carboxylic acids are brominated by a mixture of bromine and phosphorus tribromide, which is called the Halogenation reaction. So, in terms of the actual reactant and product, we start with a carboxylic acid and we end with an alpha brominated carboxylic acid. However, mechanistically, there's a lot happening in this reaction, and if you're clever, you can leverage that and use your understanding of the mechanism to modify this reaction. Okay, so we can break down this reaction into three distinct stages. First, we are preparing the acyl bromide via a nucleophilic acyl substitution reaction. Next, we tautomerize our acyl bromide to the Enol Tautomer. And in the third step, we brominate our Enol Tautomer with bromine. Finally, to re-isolate the carboxylic acid, we hydrolyze our acyl bromide with water. So these are the main discrete parts of the Hell-Vollard-Zielinski reaction. And now what we'll do is we'll show the mechanism for each of these steps. Okay, so in terms of the mechanism, I'm going to label this giant alkyl group as R. So we have R, CH2, and then our carboxylic acid, okay? And I'm leaving the alpha position drawn out clearly because it's very important in this reaction. So for the first phase of our reaction, we're going to convert this carboxylic acid into an acyl bromide via reaction with phosphorus tribromide. Now this mechanism is going to look almost identical to the thionyl chloride mechanism that we've seen in previous chapters. So our carboxylic acid, which is nucleophilic, will attack the electrophilic phosphorus atom in phosphorus tribromide. From here, we will generate this highly activated leaving group. And now our carbonyl carbon has been primed for reaction with even weak nucleophiles such as bromide. So bromide will attack, and that in turn will give us a tetrahedral intermediate. Now, the interesting thing, just like with thionyl chloride, we now have this highly activated leaving group. So rather than kicking out hydroxide or bromide, we're going to kick out this activated leaving group. From here, we now have this protonated acyl bromide. And this acyl bromide can then be deprotonated in our cleanup step with bromide. Okay, so we're at the end of our first step, and I'm not going to deprotonate my carbonyl oxygen because this intermediate can actually be immediately used in the next step. Is everyone following with me so far for this first step where we convert our carboxylic acid to an acyl bromide with phosphorus tribromide? It's a functionally identical mechanism to the thionyl chloride mechanism that we've seen in previous chapters. Can I get some confirmation that everyone is following along so far? Any questions so far in this mechanism?
In the very first step, where is the phosphorus getting attacked from? Is it the lone pair or is it?
It's technically the electrons in this double bond, and it's being, these electrons are being used to form a phosphorus oxygen single bond.
Okay.
Does that answer your question?
Yes.
Perfect. So now that we have our protonated acyl bromide, if we wanted to make our Enol Tautomer, now that we have an acyl bromide, it's easier and substantially more, it's substantially easier to generate the Enol Tautomer via just straight deprotonation of the alpha position. When we have a carboxylic acid, the carboxylic acid proton is the most acidic proton. So it's difficult to form the Enol Tautomer under the reaction conditions. When we have the acyl bromide, formation of the Enol Tautomer occurs readily. From here, now that we have our Enol Tautomer, which is nucleophilic, can react with common electrophiles such as bromine to generate the alpha brominated product. So that in turn gives us our desired alpha bromo acyl bromide. Now, in order to isolate our desired carboxylic acid product, what we are going to do is we are going to hydrolyze this acyl bromide with water. One point that I'd like you to note is you can use any nucleophile that you want within reason. So in this case, we're using water as our nucleophile because we want to prepare a carboxylic acid. But just like any other reaction of an acyl bromide, if you quench with another nucleophilic solvent, you can prepare esters, amides, thioesters, really any derivative that you want. And that's part of the synthetic utility of this reaction. So, following our textbook mechanism for carbonyl substitutions, water will attack and we'll make a tetrahedral intermediate. From here, we're going to pull off a proton and kick out our leaving group. That in turn generates our protonated alpha brominated carboxylic acid. And all we have to do is pull off a proton, and that gives us our neutral product. Does this mechanism make sense to everyone? Any questions on each mechanistic step for the Hell-Vollard-Zielinski reaction? Okay then, so let's try to apply what we've learned to the following example. So in this case, we're asked to predict the product of the following reaction and draw a mechanism for this reaction. So in this case, we have butanoic acid, and we're treating it with phosphorus tribromide and bromine, followed by water. So let's try to apply what we've learned, and let's take about 5 minutes and let's try to draw out a full mechanism for this reaction. And from our drawn mechanism, let's try to predict the product for this reaction. So let's work through this example over the next 5 minutes, and then I'd like students to share their responses in the chat, verbally, or annotated on the class whiteboard. So we already have a student starting to share their proposed mechanism on the class whiteboard. And as students work through this mechanism, don't be shy to share your thoughts in the chat or share your questions in the chat. So in this case, for our first step, we're going to attack the electrophilic phosphorus atom of phosphorus tribromide with our nucleophilic carboxylic acid. From here now, reaction with phosphorus tribromide. Would you be able to draw the phosphorus tribromide adduct? Could you draw the oxygen phosphorus bond and show how we've activated our alcohol as a leaving group? We lost the bromine, so there are only 2 bromines attached to the phosphorus. In either case, we've now activated our carbonyl carbon so that even weak nucleophiles such as bromide can attack that carbonyl carbon. So our nucleophile is going to attack the electrophilic carbonyl carbon. And from here, we're going to generate a tetrahedral intermediate. So now in this case, rather than losing bromide or losing an equivalent of hydroxide, we can kick out this highly activated leaving group to form our acyl bromide. I would show loss of the leaving group by breaking that carbon-oxygen bond. So here now we've generated our protonated acyl bromide. Okay, so we've cleared the first step, which is making our acyl bromide. And the reason why we're going through the acyl bromide is that it allows you to readily generate the Enol Tautomer. So what happens next? How are we eventually going to brominate this compound? Would anyone like to continue on with this mechanism on the class whiteboard, or would anyone like to share their thoughts for how we can complete this mechanism? You can also share your proposed comments in the chat, and I'd be happy to annotate your responses onto the class whiteboard. So from here, as we have this highly activated alpha proton, we're going to pull off that proton with a base. Wonderful. That in turn will generate our Enol Tautomer. Now that we have this Enol Tautomer, it can readily react under acidic conditions with a range of electrophiles such as bromine. So our Enol Tautomer will react with our electrophile, which in this case is bromine, and generate our alpha brominated acyl bromide. From here, we then have to hydrolyze our acyl bromide back to the carboxylic acid via a textbook carbonyl substitution reaction. So water will attack our activated carbonyl carbon. From here, we're going to lose our leaving group, which in this case is bromide. From here, all we have to do is one last cleanup step, where we pull off a proton, and that gives us our neutral isolable alpha brominated carboxylic acid. Perfect. So this student proposed mechanism looks great. It's wonderful to see multiple students sharing their proposed mechanisms. So what I'm going to do is I'm going to re-annotate these student mechanisms on the class whiteboard so everything is shared when we export this note set. Okay, so reiterating the key steps for this mechanism. First, we have to convert our carboxylic acid into a acyl bromide product. So from here, our nucleophilic carboxylic acid will attack the electrophilic phosphorus and phosphorus tribromide to generate this activated leaving group. From here, our carbonyl carbon has now been activated by these electron withdrawing groups so that even weak nucleophiles such as bromide can attack the carbonyl carbon to form a tetrahedral intermediate. Now, rather than simply losing an equivalent of bromide, in this case, we can lose our activated leaving group and kick out this activated leaving group to generate our desired acyl bromide product. Okay, now from here, we're ready to tautomerize this acyl bromide to the corresponding reactive Enol Tautomer. Deprotonation of the alpha position yields our Enol Tautomer. And this Enol Tautomer can we react with common electrophiles such as bromine to generate the alpha brominated acyl bromide. From here, in order to regenerate our carboxylic acid, we're going to hydrolyze our acyl bromide via treatment with water. I would note for this last step, really any nucleophile can work as long as it's competent in a carbonyl substitution reaction. From here, as a last cleanup step in this carbonyl substitution reaction, we're going to kick out our leaving group, which is bromide. And that in turn generates our protonated carboxylic acid. All we have to do as a cleanup step is deprotonate, and that gives us our neutral isolable alpha brominated carboxylic acid. Any questions on the mechanism for this reaction? So we're at a reasonable stopping point for today. So what we'll do is we'll archive this recording.